The Sun and its atmosphere. First, we're going to look at some of the general characteristics of our Sun. And the first thing to know is that our Sun is a star, and obviously it is our closest star. In terms of light travel time, our Sun is 8 light minutes away. So it takes light 8 minutes to travel from the Sun to the Earth. In comparison, the next nearest star is about 4 light years away. So think about how 8 minutes compares to 4 years. That's the difference in distance that we're talking about. And that difference means that our Sun is really going to be the only star we can study in detail. And so we can use our Sun as a starting point for understanding all stars and be able to compare other stars to our Sun. The other thing is our Sun's composition. Our Sun is primarily hydrogen. Recall that H stands for hydrogen, 73% hydrogen, 25% helium. He stands for helium. So that adds up to 98%. So what's that other 2%? Pretty much every other element that we know about. Now the pie chart here shows some of the things that are slightly higher in abundance. So we've got oxygen, carbon, neon, nitrogen, iron, magnesium, silicon, sulfur, and then everything else in the periodic table. So our Sun does have all of those elements, but what dominates it? Hydrogen and helium. What we can see of our Sun is called the solar atmosphere. So this is our observable part of the Sun. And the photosphere is the lowest layer of the Sun's atmosphere. When you glance at the Sun, everyone knows you're not supposed to look at the Sun, but sunrise, sunset, you happen to look up and there it is. The photosphere is the part of the Sun that you are seeing. And the name photosphere literally means a circle of light, because this is the part that the light that we see comes from. And when we look at the photosphere, in detail, we can see a number of features. And one of the features that we can see is called granulation. And that's this grainy appearance to the Sun. This is highly magnified view of the photosphere, and we see all of these little things that look like grains. It's often described as looking like grains of sand. And what we are seeing is that the white parts is where it is hotter. That color is not showing up well, neither is the green. Let's try red. The dark parts is where it's cooler. And what's happening is the hot material is rising and the cool material is sinking. So we are seeing basically the boiling of the Sun's surface. And so you're seeing material rise and sink in the same kind of motion that you see in boiling water. Another feature we see on the photosphere are called faculae. It is not these things. We're going to talk about those in the next slide. What we're looking at are these lighter features over here. And so these light features are actually places that are hotter, which is why they look white against the background. And these are regions where the magnetic field is distorted. And so the more distorted the magnetic field, the more faculae you're going to see. We tend to only see them near the edge of the sun. The edge of the sun is called the limb. And that's because it tends to be a little bit darker, and that's an effect of the fact that our sun is a ball. And so when you're looking towards the edge, you're not looking all the way to the center the way you are when you look towards the middle. So it's going to look a little darker in the background. And so with the darker background, these brighter spots stand out. And so that's why we see them there. They're really everywhere, it's just they're easier to see towards the limb. Those dark spots that we saw in the previous image are called sunspots. So these are dark regions. And being darker tells us that they're cooler than their surroundings. And this is also due to magnetic field distortion. And there is a separate tutorial all about distortion, about how sunspots form and how it's related to most of the features that we'll be talking about in the solar atmosphere. But for now, we just want to talk in terms of what we know about sunspots in appearance. To get you a sense of scale, this sunspot right here, that little black spot, that's about the size of Earth. So it gives you a sense of how big the sun is compared to Earth, but also how big other sunspots are, because something like this is about 3 to 4 times the size of the Earth. So we're talking about very large features here. And they are not permanent. Sunspots last anywhere from a few days to a few weeks. Depends on the size. The bigger ones last longer than the smaller ones. And our sun rotates. So one of the things we'll see is that as the sun rotates, the sunspots will change position. So each day they'll be shifted a little bit due to that rotation. The chromasphere is our next layer out. And that literally means circle of color, because it does have a red color to it. This was first observed during solar eclipses, because during a solar eclipse, of course, the moon is blocking the sun. And in particular, the moon is blocking the photosphere. So it's blocking the part of the sun that gives off all that light that we normally associate with the sun. But because it's blocking the photosphere, it means we can start to see layers outside of the photosphere. And we see a very thin layer of red that will appear during a solar eclipse, and that is the chromasphere. Now we can also use special filters. It's called a hydrogen alpha filter, which basically means that it is blocking out all light except light that has the same wavelength as the alpha line in the hydrogen spectrum. So basically that means we're using a red filter. It's a very narrow part of red, so it's not showing all parts of the red spectrum, but just the part associated with that particular emission line of hydrogen. So it dims it down because we're not letting through all the light from the sun, we're just letting through this one wavelength of light from the sun. When we look at the chromosphere, one of the things we'll see are prominences. And prominences, this is an amazing prominence here. This is, I think, the largest ever observed prominence. But what we are seeing, as it says here, are kinks in the magnetic field. So you're actually seeing the magnetic field line bulge up and out away from the sun. And you will find at the base of that sunspots. So it is connected to the sunspots. Now, like I said, that is an insanely large prominence. These little bumps you see over here, these are typical sized prominences. So normal sized prominence, insane prominence. Also associated with the chromosphere are flares, also known as solar flares. And so that same kink that we just saw with the prominence can break. And when it breaks, you're going to have material shoot away from the sun. And that's a solar flare. So it's going to look bright because it's shooting out material. And you will get charged particles shot out. If those come towards Earth, if it happens to be aimed just right, on Earth it can create aurora, which are also known as the northern lights, which are very pretty. Well, it can also wipe out satellites and electrical grids. So if it's a really strong solar flare, it can be quite dangerous. It is dangerous to astronauts. So for our astronauts, we let them know, astronauts, if a solar flare is coming, they have safe places they can go in the space station. But that is a solar flare. The corona is the outermost layer. And again, in the case of a solar eclipse, this is the dramatic part that you can see in a solar eclipse, where you see what looks like streams of material coming out from the sun. That is the corona. And one of the things associated with the corona is the solar wind. This is a stream of charged particles constantly coming from the sun. So that's what's being illustrated here. So, we have the solar flares where it's this sudden outburst, and that's a very strong burst of charged particles. This is much more benign. And it has to do with the fact that the sun is so hot. And so the outermost part of the sun basically evaporates isn't really the right word, but it's, constantly being pushed off. And so the illustration here is showing it does interact with our magnetic field. This is Earth's magnetic field here, and showing our magnetic field lines. And if those charged particles get funneled down to the poles, that's when we get aurora. And so if there's a sudden burst, then you get more charged particles and you get stronger aurora, and you get a really nice light show. Can't emphasize enough this picture, not to scale. The Earth is most definitely not that close to the Sun. On the corona is actually very hot. Of the atmosphere layers, it is actually the hottest of the atmosphere layers. It's about 1,000,000 degrees Kelvin. And recall that the photosphere is about 5,800 degrees Kelvin. So very, very hot. And that's due to energy from the magnetic field is what heats up the corona. But because it's so hot, we can see it in the X-ray part of the spectrum. That's actually where it radiates the most. Now, we can't observe X-rays from the surface of Earth, so we use orbiting satellites to observe in the X-rays. And that's what this picture is. This is an X-ray image of the Sun. And the coronal holes are these bright spots. Those are holes in the corona. And as you see, this is where the solar wind has its origin, because that's letting the material out. And so it's acting as a little hole, a little escape valve for that hot material. Corona also experiences what are called coronal mass ejections, or CME for short. And these are violent eruptions. They are associated with solar flares. And the breaking of magnetic field lines, plural. And so in this case, not only is it charged particles, but actually gas that is erupted. And so these bright things that you see here, those are actually being shot out of the corona. Those are the coronal mass ejections. And again, if these interact with Earth, we're going to get aurora. We can get satellite damage if it's really powerful, and if the satellite isn't protected properly. It can affect power grid, so you can get power outages. And of course, astronauts can be affected by it as well. So beautiful to see, but very, very dangerous things that can come shooting off of the Sun if we happen to be in the line of fire. So that's the Sun and the part of the Sun we can see, which we call the solar atmosphere.